Hello all, I Debushree Das on behalf of our team will be presenting the paper DriBe on-road mobile telemetry for locality-neutral driving behavior annotation. Before we start, let us consider an example of a typical driving behavior scenario where the driver is adhering to the road safety rules, keeping a safe distance between adjacent vehicles. Thus, the driving behavior depends a lot on the driving skill of a particular driver, as he has to handle the maneuvers, road conditions, etc. However, just while maintaining a safe distance, what if the front vehicle took a sudden brake and the following vehicle, called the target vehicle, has to force a brake to avoid collision? According to driving safety rules, the sudden brake will be tagged as dangerous. But is it really the driver's fault? No, right? Now, these driving rules vary a lot across countries. For example, the driving maneuver itself will vary according to left-hand or right-hand driving rules. Similarly, speed constraints, inter-vehicle distance, and so on varies around the globe. For example, suppose overtaking in one country is an usual practice and comes under safe maneuver due to the non-crowded traffic. But it does not mean that in another traffic congested country, it will be considered as safe. So if we make a driving score prediction model based on the former country, it may not correctly estimate the driving score in the latter country due to the diversity in driving signatures. So this day-to-day scenario motivates us to dive into this problem of driving behavior score annotation by investigating the reasoning behind certain driving maneuvers. But the research question lies here is how to find the causes behind such maneuvers. Existing literature that worked on driving behavior analysis uses the modalities such as information from a connected vehicular system or traffic surveillance camera, physiological sensors or IMU sensors from a smartphone. But getting information from a connected vehicle needs high infrastructural support. Moreover, vehicles might not want to share their information until and unless there is a government policy. Another challenge goes with the traffic surveillance camera is that we will get the information for a particular region, but with a moving car, the information gets static. There are other modalities as well. For example, the physiological sensors, which mainly assess the effect of stress on driving behavior, but again, no one would like to wear this much of sensors while driving. We can use the IMU sensors also, but it will sense the maneuvers of the drivers only, not beyond the vehicle. Moreover, existing works consider the data to be independent and identically distributed. So, we need to develop some sort of system which runs on each vehicle independently, a non-intrusive one, dynamic and location invariant in nature. For this, the solution lies in our handheld devices only. That is, we can use the rear camera of the smart device mounted on the dashboard of the vehicle to sense the surrounding beyond the car. Along with this, we can use the knowledge of one existing model to enrich using another location's data and also cross-verify it through the trip score given by the commuter. Therefore, our objective is to develop a proof of concept model which will run on each vehicle independently and use the IMU and GPS data to understand the driving maneuvers. The smartphone's rear camera will be used to infer the impact of causal factors. Following this, we transfer the knowledge of one location and reuse it to learn driving behavior in another location. Finally, it will provide a driving behavior score in a Likert scale of 1 to 5. Next, we briefly introduce the public and in-house dataset used in our study. For the public dataset, we use the Berkeley Deep Drive dataset, which consists of 100K trips. Each of the trip consists of 40 seconds time window and has IMU, GPS and video data captured through the rear camera. BDD dataset covers two countries, that is USA and Israel. We collect the in-house data over India. We recruited 8 participants who had at least 5 years of driving experience. We collected 20 trips over 7 days, comprising IMU, GPS, and video data captured through the rear camera of a smartphone. Although the PDD dataset used here is a content-rich dataset, but it is not annotated on how the driver drives or specifically the driving behavior score. So we launched a VR application to annotate the dataset. This application shows driving video clip and prompts the annotator to give a score in a scale of 1 to 5, asking how the driver drives on every 5 seconds. In this way, we received annotations for 4,000 trips by 46 annotators. Now, to understand how can the front vehicle impact the target vehicle's driving behavior, let us consider two drivers D1 and D2. First, we plot the forward movement of both the front and the target vehicle in terms of y-axis accelerometer data over 40-second time window. We can see that for driver D2, the maneuver B22, the front vehicle is decelerating sharply, possibly taking a sudden brake, and it is also compelling the target vehicle to decelerate. However, for D1, the front vehicle takes a moderate brake and consequently the target vehicle decelerates sharply due to the sudden brake. Thus, we see for B22, although the front vehicle was responsible for the bad driving, but for B12, it was due to amateurish driving. But the existing literature will tag both of them as dangerous. Thus, identifying the causal factors and its impact is really necessary. Next, to understand whether there is a scope to build a universal model for auto-annotating the driving behavior, we dive into feature study. First, we calculate the Spearman correlation coefficient among different features such as jerkiness, turns, stops, relative speed, and distance. From the figure A, we can view that although the stop is positively correlated in USA, it's negative in Israel. Basically, in Israel, sudden stops influences jerkiness, thus lowering the score. Whereas in USA, this behavior is seldom. Similarly, the feature variation among the two countries shown in figure B strengthens the need for a location-independent model development. Now, there can be multiple surrounding factors influencing the driving behavior, but we need to judicially select the causal factors. For this purpose, we perform a statistical test called causality analysis using average treatment effect. First, we divide our feature space into two, namely impactive features. Basically, it holds the driving maneuvers such as abrupt stop, sharp turns, changing the lane, etc. And the next one is the causal factors such as braking behavior, relative speed, distance, congestion. First, we do a correlation analysis among these features and the driving score using tau coefficient, and then keep the features with correlation having at least 0.4. Next, using average treatment effect, we keep only the features having score at least 0.5. The intuition behind this is that these features directly impact the driving behavior. So finally, our impactive features set comprises abrupt stops, sharp turns, and severe jerkiness. And the causal set becomes the front vehicle's braking action, relative speed, and distance variation. Now we present our overall system architecture, which is DriBe. The first component is the data collection and the pre-processing, where we make the system noise-free and the video data resolution invariant. In the second step, we extract both the impactive and the causal features. For this, we use the standard accelerometry analysis to detect the sudden brakes and severe jerkiness. For sharp turns, we use turn angles from latitude and longitudinal components of GPS. From the video data, we detect the braking action of the front vehicle and relative speed and distance variation between the front and the target vehicles. To detect the braking action of the front vehicle, we track whether the brake lights of the vehicle are on or off. Once we detect the front vehicle using the Hawk descriptor, we apply color transformation to highlight the brake lights. And after that, we use a 8-layer CNN to classify whether brake lights are on or off. Next, we use perspective transformation to detect the distance between the front vehicle and the target vehicle. Once the distance is detected, we multiply frames per second with the change in distance to get the relative speed. And in the last module, we design a domain adaptation technique to achieve location neutrality in predicting the driving score based on the impact of causal factors. So the architecture is as follows. First, we train the model over the source country dataset using a feed-forward neural network of 4 dense layers, followed by 1 dropout layer and 1 classification layer. We call this as the bootstrap model. For minimizing the loss between the predicted and the ground truth score, that is the out cap and the out, we use categorical cross entropy function. Next, to capture the difference in training data over the target country, we freeze all the layers except the last layer, which is the classification layer. And the bootstrap model will identify on which data it will need retraining in this layer. However, in the target country, we do not have the ground truth labels against the on-the-fly data. But we can utilize the commuter given score, that is RG target, against each trip for retraining. But this RG target can be biased due to human intervention or indifference. However, we can cross-verify that also. The impactive features gives a driving score, which is a location-independent score, as claimed by the existing literature. Thus, we train a model MI over the source country and use it to predict the driving score RPI over the target country using their impactive features only. Next, the RG target having high correlation with the RPI are chosen as the valid labels and further considered for retraining if the bootstrap model misclassified the training instances. In this transfer learning architecture, during retraining, the distance between the source and the target country's feature maps are minimized using the Manhattan distance. Finally, softmax is applied to generate the highest probable score in a Likert scale of 1 to 5. So once the model DriBe is developed, we introduce our evaluation setup. USA is used as a source country, whereas Israel and India are considered as the target countries from the in-house and the public dataset. The dataset is split into 70:15:15 for training, validation, and testing for the source country. We report the micro F1 score of two cases. In the first case, we directly run the bootstrap model on the target country dataset without retraining, and in the second one, we use retraining. From the figure, we can observe the micro F1 score increased from 0.55 to 0.72 for Israel and 0.41 to 0.62 for India for without and with retraining. For the rest of the results, we use the Israel dataset to report the performance. Next, we perform an ablation study to show the importance of causal factors in our model. We keep impactive and braking action of the front vehicle in drive speed. In drive braking, we keep the impactive and the relative speed and distance component. In the drive causal, we keep only the causal features, and in the last variant of drive impactive, only the impactive features are kept. We observe a sharp drop in accuracy excluding the causal factors, which further establishes the fact that causal factors contribute superiorly in predicting the driving score. However, if only causal factors are considered, the accuracy is worse as it is the influential features and need a base to work upon. This concludes the importance of impactive features as the fundamental one. Next, apart from the different location, we show how the domain adaptation technique will perform on different road scenarios. For this, we train the bootstrap model over smooth, congested, and bumpy roads as source and use with and without retraining architecture. We see for the similar road scenario, for example, congested or stops, quick performance gain is there. However, for dissimilar scenarios, such as smooth or turns, it takes time and the gain is lower. So, we developed DriBe, a system by exploiting different modalities and a domain adaptation architecture to introduce location neutrality in predicting the unbiased driving score. In addition to this, we can extend this work to incorporate other information such as pedestrians, traffic signs, traffic lights, and many more, which can infer the context behind improved or degraded driving behavior. Another direction can be incorporating weather and time of the day information. For example, during nighttime, drivers tend to behave recklessly due to light invigilation, vacant roads, etc. But during nighttime, heavy vehicles such as truck, bus, those movement also increases, which is dangerous in case of reckless movement. So with this, we conclude our work. Thank you for listening to my talk. I would like to hear if you have any questions in your mind.